This is a presentation by Hartmut Opfermann, and he's talking about a large OB truck that they built for an Austrian broadcaster. All IP, it's a fascinating system. So without further ado, take it away, Hartmut.
Yeah, thank you very much, Wes. So, Wes said we built it. We are just building it. It's in our facilities in Mainz, in Germany, where BFE headquarters is located. There is this big 40-ton truck being finished with everything that makes up a large OB truck. We're laying cables, everything. So just to give you an overview of what I will be talking about, I will tell you a little bit about who the customer is of this OB truck, what the task was that we were given as a system integrator, then the decision, obviously, do we do it in IP, don't we do it? The challenges we faced during the project so far, and then I wrap it up with a conclusion. So the customer is ORF. It's the public broadcaster in Austria, and Austria has roughly 8 million inhabitants, so that's the viewing population that can view the programs, which are 24/7 TV channels for Austria, and 9 regional channels which are only broadcast part of the day, and then additionally 12 radio channels. And for these programs, ORF decided that they had to rebuild one of their OB trucks, one of the large ones. And there were several premises that they made. Of course, first and foremost, it must be a cost-effective solution. It's funded by public money, and you have to take care of taxpayers' money so that you do not build something that's expensive. And with this goes that some equipment from the old truck that needed to be replaced was reused because it was not deprecated. It just, you don't throw it away, but you reuse some of the equipment, which was one of the constraints we were given. And then with this, the operator's workflows shouldn't change. When you build a new system, you have two ways. Either you want to keep your old workflows, or you make a deep analysis. What do you want to do? How should your workflows look like? In this case, the decision was that the workflows should be the same. So then that also limits what you can do, obviously. And it needs to work with the existing infrastructure. Obviously, even though a OB van is a self-contained unit, sometimes you want to connect it to your facility. You need to replace a control room that you have, and you want to have the OB van stand in, and so on. So it needs to work with the existing infrastructure, still SDI based, and the design needs to be scalable. So if we have a new design here in this OB van, maybe in the future there will be larger projects, like in the facility, in the headquarters themselves. So whatever we do in the OB van, if it's a new design, then it must be scalable to fit the needs of a larger facility. Oops. So now the decision. Obviously, currently it's still a big decision if you go classical. We also have customers who still build SDI facilities, or if you do it via IP. In this case, our customer ORF asked us for 3 options, which we priced and quoted. One was based on a traditional SDI-based router, one on a proprietary networking technology, and the third on a standards-based IP deployment. And of course, there were some decision criteria, and as you can see from the criteria which are listed here on the slide, they are not really hard criteria. It must be economically viable. It's not it must be the cheapest or something like that. But of course, as I said, economics is a key factor. But sometimes if you get more, you're willing to pay more, but it still must fit obviously into your budget. Of course, functionality that you need, and it must have a certain maturity. I don't say it must be on the market 5 years. It would be easy to rule out a lot of IP equipment if you make that proposition, but you have to have at least you have to believe that what you see is capable of doing what it needs to do. One of the things that our customer also said is that we have this new IP technology, and if possible, we may want to learn more about it. So we do not just build IP systems just for the sake of it, but it's a new technology, and you learn about the technology the most if you do a project with it. That does not mean that you can do a project with any technology, but if you look at a specific technology, it's good to have a limited project with it just to learn more about the technology. You just do it for the sake of it. And then another decision criteria was the flexibility. So although this truck is currently built for the standard that's currently in use at ORF, which is 1080i 25, in the future, probably at some point in time, 4K will come along also for ORF, and they do not want to rebuild the complete OB truck, but want to be able, with very less effort, to upgrade it to 4K. And of course, as things are changing more and more, you want to be able to upgrade the functionality of the OB track relatively easy. So that was the decision criteria, and probably I wouldn't be standing here if the decision would not have been, we go for IP. And so after a careful consideration, so it was really some months where we looked at these different options, it was decided that yes, the technology is mature enough to do this truck in IP. So now we come to the interesting part, the challenges. There's a lot of challenges. First of all, you need SDI to IP converters. Currently, especially for an OB truck where you have to connect to outside world to other OB trucks, you cannot do IP system. There's always some SDI equipment around here. Yesterday I heard a discussion with Andy Bechtolsheim of Arista, and he said that he believes that SDI is around here for another 30 years, and that's coming from Arista. So you need SDI to IP. But why is that a problem? Of course, it is a problem. You need more equipment. So does it cost more to do this with SDI to IP converters? And the other thing is you have to have the seamless experience, like the workflows for the operators should not change. So what do you do with SDI to IP converters? We were there before. So what do you have to do to tackle this? The good thing is converters are often integrated into processing equipment, and you need your processing equipment in the truck anyway. So you do not have additional devices, and you have very small additional cost for the converting. And all the other way around, if you buy the converters, you get your processing not for free, but it's integrated. And another thing that we learned as we discussed the detailed design of the system, that you can save a lot by moving to newer equipment, and we had the luck that during our phase, some new equipment was coming out, or newer versions of devices that we wanted to use, which had native IP interfaces, and so we were able to drop the number of of IP to SDI gateways that we originally anticipated by 1/3. So this is really a big decline, and I think this is obviously going on and on as more and more devices with native IP interfaces are coming out, so that you will need less and less gateways. And of course, you have to have, if you have a good control system, broadcast control system with an SDN controller, then this is able to provide a seamless experience across all these gateways. Next challenge. The next challenge, devices are evolving rapidly. This is not new. The devices were evolving rapidly for quite some time, but with IP, it's still even faster, as this is a new technology, and if the technology is very new, then more quickly. There is, as we have seen, devices with new IP-capable boards, or even new devices, new versions of devices which are IP-capable, so that you can save some of the SDI interfaces. There are new software versions. All these IP devices, as they are quite new, they get frequent updates, and sometimes you have to have an update just to give the required features that you have. And there are also new control interfaces coming along. Some of the devices that we got are not NMOS compliant, but in the future they will be, so you have to constantly, or you could constantly upgrade your device, but at a specific point you have to freeze your design just to be able to build a working system, and I have to defer some upgrades to a later stage when you go back and redo things. I think, yeah, we will come to a stage where we more frequently do upgrades of systems. Next challenge, defining software-defined hardware. Now, what is software-defined hardware? As you walk around the show, you see a number of vendors coming out with FPGA-based processing equipment, which is, as it is FPGA, field programmable gate arrays, which can be programmed in the field, like not at the factory, with functions upgraded with newer functions. And so what the device does is dependent on the software, but can also be dependent on the configuration. Each vendor has to make a trade-off on how much flexibility he builds into the device, because if it's more flexible, then it's more difficult to configure, and if it's more rigid, like it's not that flexible, then lack maybe some flexibility, but then it's not so difficult to configure. In our case, as I said at the beginning, the flexibility was one of the key decisions. So in this case, we opted for a device that was could have a lot of different options, a lot of different configurations, and that means configuration. So we tackle this. What you have is essentially with this device a subsystem in a box. Yeah, it's like a tool set where you can define how many routers you want to have in those boxes, how many color correction units, and so on, and how you want to connect them. And this gives you a lot of flexibility for work in different scenarios. You have to somehow constrain this flexibility, and because if each of the different differently, then it's very hard to manage. And in this case, we had 37 of those flexible devices, and we managed to come up with a very limited number of configurations that we needed. Actually, we had three. One where the device was working as a multi-viewer, then one where there were 18 ins and 2 outs for things where we had a lot of inputs like cameras and so on, and then where the ins and outs were balanced. And all these different designs had various processing equipment configured in it, but we did not use everything because we did not need it at any place, and therefore we did not need to buy the license for every of the 37 boxes. But it was a good thing to have a very limited number of configurations to keep the system manageable. Next challenge, IP address management. This is something that's really new for IP. You have IP addresses. You didn't have that in SDI. And currently, this is for the system we are building now. It's a manual task, and it's a lot of work. It's a long list with all the IP addresses, unicast, multicast addresses, and you have to very carefully manage this, not to break things. But the future will be better, not for this project, but the next project. You can automate a lot of these things by using DHCP for the unicast addresses and NMOS ISO5 for the multicast address.
You want to get louder?
Yeah, for giving out the multicast addresses. This is very neatly laid out in the JTNM TR 1001-1 document, which I
2 out of 3.
recommend reading. The next challenge, audio channel management. Why is this an audio channel management challenge? We had, in the old days, we had very fixed signals with a very fixed number of channels. Like if you had a standard AES-3, that was 2 channels. If you have a MADI, it was 64 channels. With IP, it's different. You can have virtually any number of channels in an IP stream.
Okay.
How many channels do you want? You could have 1 audio channel per stream, which would give you a lot of flexibility because you can route your channels individually through your network. You could have more channels, then you would have less streams, which puts less burden on your switches. There is one boundary, which is the 8, because the minimum requirement for SMPTE 2110-3 is what is called level A, and it limits the maximum stream numbers to 8. So if you go over 8, you're out of the minimum requirements, then you have to check with every device if it supports more than 8 channels. Then there is this thing about stream receivers. Some devices have a limited number of stream receivers. So if you have a lot of multicast streams, you could easily run out of stream receivers in one receiving device. Other devices have a limited number of channels that they can receive. And I will go deeper in that on the next slides of what that means. What we did in this particular project, we chose the channel, the default number of channels at 8. So this is what it could look like if you have a number of devices, all streaming 16 audio channels into a device. And you have 1 audio channel per stream, then this is 16 streams for each device, and you need 16 times number of devices, receivers. And that's like if you have a device that has 80 receivers, then you can only have 5 devices feeding into it. Now say, okay, I want to do it different so that I can make better use of my receivers, and you have only 1 stream for 16 audio channels, then you need only 2 times the receivers. But if your device has only 2 audio channels that it wants to send, and you have your standard audio channel bandwidth, audio channel width sent to 16, then the device B has to allocate n times 60 audio input channels if it cannot select the channels from the streams. And so you run into a problem here. And so what we did is we set the audio channel per stream, and for devices where we had this problem of balancing receivers and audio channels, we had a special audio shuffler or an audio shuffler put in between who selects the channels to send out to the device. So, next challenge. How to switch on and off. Why is that a challenge? I mean, it's something we had with OB vans before. You have to, in contrast to a fixed system, you switch your OB truck on and off frequently. Why is that different now? We look at an old SDI router, you switch it off, you switch it on, it comes back exactly as it was before. Why is this? It's a system, also modular of any kind, but there is a controller in there who takes care that everything is configured when it comes up as it was before. So how is this different with IP? You do not have the green box anymore, because now everything is distributed. You have an SDN controller, you have a sender, different senders from different manufacturers, we have receivers from different manufacturers and switches from still another manufacturer, and you have to make sure that your SDN controller is capable of recreating the same stages as it was before when you switch on the OB truck. And still more, training. Training comes up very frequently. In this case, we had training always. There were always new devices, new topics, even in the SDI world. But what is different now is that some very basic fundamental things are just different. And this expands the training requirements that you have. There are more things. I mean, you didn't have to teach somebody how SDI works in a facility. But you have to train people at least basics about how IP works. And because of that, there's a lot of uncertainty with the people that will be operating these systems. And part of the training is giving the people the certainty that they can work with these devices and also that they can troubleshoot this, because troubleshooting is also different. Like, you cannot just plug in another device into some switch port like you did with a SDI-based router and expect it to immediately display the signal that's coming out of that port, because there might be several signals coming out of that port. And this is something that all the operators have to learn and that you have to provide training for. Synchronization. Synchronization is different with IP. You can learn it everywhere. But what are the special challenges with this? I mean, of course, everyone has to implement PDP, and it might be not flawless in every implementation. But apart from that, PDP requires more configuration. What configuration did you need for Blackburst? You just plugged in your Blackburst and it worked. Currently, it's not a lot of, but it's a manual configuration that you have to do on each device. But also the document I mentioned before, JTNM TR 1001-1, addresses this with a system resource that you can have on your NMOS registration server, which centrally provides all these configuration data. Just make sure, as long as you do not have this, that you configure your PTP correctly on all the devices. Another thing, as long as you do not have a pure PTP-based system, as you have a lot of SDI equipment, you're also going to have Blackburst. And you need to make sure that your PTP and Blackburst stay in sync. And there are two variations of this. What happens if you do not have PTP available, no GPS reception, because you're in a tunnel, in a underground somewhere, but you have a Blackburst that you have to sync to. Then it is well defined in an engineering guideline from SMPTE, but it's only an engineering guideline. There are devices that behave differently. Usually your PTP from your sync generator should be aligned directly with the PTP, with the Blackburst that you receive. Even if it's not the exact correct time, it can be off 10 milliseconds, but
absolutely. Yep.
But it should always align. But not all devices do this, as we had to learn. And then redundancy mechanisms for PDP and blackburst are not always aligned. So look at this picture where we had two SPGs and PDP generators, and this is how it is in a good case. Yeah? We have some priority set on the PDP generators, and PDP1 wins the best master clock algorithm, which decides which one is the real master of the two. And we have a switch for the blackburst, and it looks at the blackburst signal and says, both blackburst signals is valid, I'll take the first one. That's just how you configure it. So now your blackburst fails. PDP doesn't know about this, your blackburst output. PDP says it's everything like before. PDP1 wins the best master clock algorithm, the other one stays quiet, but your switch, it has notified the blackburst has failed and just switches to the other SPG. Now, blackburst comes from SPG2 and PDP comes from from SPG1. It's not a big problem because both are synced to GPS, but it's difficult to manage. Now, guess what happens if the GPS fails? Then PDP, the PDP generator in the SPG, will lower its clock class. It would say, my clock is not as good because it's not locked to GPS. Then the other one says, oh, I have the better clock class, I'll take over. Now you receive PDP from SPG2. What does the switch say? Both blackburst signals are good, I'll take the first one, and now you have a problem which is really nasty because now blackburst comes from one source which is not locked to GPS but runs on its internal oscillator, and the other, the PDP, comes from the PDP generator which is still locked to GPS. And then you will have a drift over time. You can be lucky that you switch off your OB van before it really gets annoying. Okay, we discovered this with the sync generators we were using, and we asked the vendor, what do you do? The vendor said, buy more of my equipment. You can have two separate SPGs that generate the PDP, and you have another set of two SPGs which generate the blackburst from the PDP. Then the PDP blackburst is guaranteed to be synced to PDP. Okay, additional money required, and what's even worse is you need more space, and that's something you don't have in an OB truck generally. What we came up with a solution, we had our control system manage this and have it follow the blackburst changeover unit by manipulating the PDP priority. I was very reluctant to do it because I don't like fiddling with the PDP priorities, but it's the best and fastest way to have them fail over. Actually, I would rather have the SPG work in a way that it always made sure that PDP and blackburst were in sync by itself. So, now the conclusion, we are in transitional period, which means we have a lot of things that we have to steer around. It's good to have a good system integrator, which knows IP as well as broadcast. IP-based production systems are viable. We had several tests, factory acceptance test. The customer was very satisfied with it. Now we're building the complete truck. And yeah, for IBC, I will tell you how it went. Yeah, we still need IP SDI adaptation and some workarounds during this transitional period. And it is essential to build knowledge about this new technology. Thank you.
Thank you, Hartmut. Are there any questions? We got time for one or two questions from the audience. Yeah, go ahead.
Hi. This switchover from PTP priority, how long does that take for the other devices to see the new PTP master and for the PTP master to take over the master role for the second one?
Yeah, the priority is sent out with each announce, and as soon as the other announce is sent with us every 2 seconds, and so after 2 seconds the best master clock algorithm starts again, and then it takes over.
Hartmut, thank you very much.
Yeah, my pleasure.